Welcome to our comprehensive guide on bipolar junction transistors or BJTs. In this unit, we'll explore the fundamental aspects of BJTs, including their construction, operation, and various configurations. Whether you're a student or an electronics enthusiast, understanding BJTs is crucial for mastering modern electronic circuits. We'll break down each concept step by step, making it easy to grasp even the more complex topics. Let's begin by looking at what a BJT is and why it's so important in the world of electronics. Get ready to dive into the fascinating world of transistors. Bipolar Junction Transistor, or BJT, is a type of semiconductor device that can amplify or switch electrical signals. It's called bipolar because it uses both electrons and holes as charge carriers. BJTs are found in countless electronic devices, from amplifiers to digital circuits. They are essential building blocks for analog and digital electronics. Understanding how BJTs work lays the foundation for more advanced topics in electronics, so let's take a closer look at their structure and operation. BJTs come in two main types, NPN and PNP. Both types have three layers of semiconductor material, but the arrangement of these layers differs. In an NPN transistor, a thin layer of p-type material is sandwiched between two n-type layers. For a PNP transistor, it's the opposite, an n-type layer is between two p-type layers. Each layer has a specific name: the emitter, base, and collector. The way these layers are arranged determines how the transistor operates and how current flows through it. Let's break down the three layers of a BJT. The emitter is heavily doped and injects charge carriers into the base. The base is very thin and lightly doped, allowing most carriers to pass through to the collector. The collector is moderately doped and larger, designed to collect carriers from the base. This structure is key to the transistor's ability to control large currents with a small input. Each region plays a unique role in the transistor's operation, making BJTs versatile components in electronic circuits. Operation of a BJT relies on the movement of charge carriers across its junctions. When the emitter-base junction is forward biased and the collector-base junction is reverse biased, the transistor enters its active region. In this state, a small current at the base controls a much larger current flowing from the emitter to the collector. This property allows BJTs to act as amplifiers, making them invaluable in signal processing and electronic communication. Though NPN and PNP transistors have similar structures, their operation differs in terms of current direction and voltage polarity. In an NPN transistor, electrons are the majority carriers, and current flows from the collector to the emitter. In a PNP transistor, holes are the majority carriers, and current flows from the emitter to the collector. Understanding these differences is crucial when designing circuits, as it affects how you connect power supplies and signal. Input characteristics of a BJT describe how the input current varies with input voltage, typically measured at the base emitter junction. For a common emitter configuration, as the base emitter voltage increases, the base current also increases. This relationship is similar to a diode's characteristic curve, reflecting the forward biased nature of the base emitter junction. Understanding input characteristics helps in predicting how the transistor will respond to different input signals. Output characteristics show how the output current changes with output voltage, usually at the collector-emitter terminals, for a given base current. In the active region, the collector current remains relatively constant despite changes in collector-emitter voltage, as long as the base current is fixed. This property is essential for amplification, as it allows the transistor to provide a stable output for varying input signal. BJTs can be connected in three basic configurations: common base CB, common emitter CE, and common collector CC. Each configuration has unique input and output characteristics as well as different applications. The choice of configuration depends on the required voltage gain, current gain, and input-output impedance. Let's explore each configuration in detail to understand their strengths and weaknesses. The common base configuration: the base terminal is shared between the input and output. The input is applied between the emitter and base, while the output is taken from the collector and base. This setup offers low input impedance and high output impedance. It's mainly used in high-frequency applications because of its excellent voltage gain and fast response. However, the current gain is less than 1, limiting its use in some amplifier circuits. Common emitter configuration is the most widely used BJT setup. Here, the emitter terminal is common to both input and output. The input is between the base and emitter, and the output is between the collector and emitter. This configuration provides both high voltage and current gain, making it ideal for amplification. It's commonly found in audio, radio, and general-purpose amplifier circuits. The common collector configuration, also known as the emitter follower, the collector terminal is common to both input and output. The input is applied between the base and collector, and the output is taken from the emitter and collector. This setup offers high input impedance and low output impedance, making it suitable for impedance matching. While it provides no voltage gain, it does offer significant current gain. Each BJT configuration, CB, CE, and CC, has its own set of advantages and disadvantages. Common base is best for high-frequency applications, common emitter is ideal for general amplification, and common collector is perfect for impedance matching. Understanding these differences helps you choose the right configuration for your specific circuit needs. Alpha, symbolized as alpha, is the current gain in a common base configuration. It represents the ratio of collector current to emitter current. Since most of the emitter current flows to the collector, alpha is typically close to 1 but always less than 1. This parameter is important for understanding how efficiently the transistor transfers input current to the output in CB mode. Eta, or beta, is the current gain in a common emitter configuration. It's defined as the ratio of collector current to base current. Since the base current is much smaller than the collector current, beta is usually a large number, often between 20 and 200. This high current gain is what makes the common emitter configuration so effective for amplification. Alpha and beta are closely related. In fact, you can calculate one if you know the other. The relationship is given by the formulas: beta equals alpha 1 alpha and alpha equals beta slash beta plus 1. This connection helps in analyzing transistor circuits, as you can switch between parameters depending on the configuration you're working with. Current gain is a key parameter in transistor operation. It determines how much the input current is amplified at the output. High current gain means a small input can control a much larger output, which is the essence of amplification. This property is what makes BJTs so valuable in audio, radio, and signal processing circuits. Load line analysis is a graphical method used to analyze and design transistor circuits. It helps determine the operating point or Q point of a BJT in a given circuit. By plotting the load line on the output characteristics curve, you can visualize how the transistor will behave under different conditions. This technique is essential for ensuring stable and predictable circuit operation. To draw the load line, you need to know the supply voltage and the load resistance in your circuit. The load line is plotted on the output characteristics graph, connecting the points where the collector current is 0 and where the collector emitter voltage is 0. This line shows all possible combinations of collector current and voltage for a given load. Q point, or quiescent point, is where the load line intersects the transistor's output characteristics. This point represents the steady-state operating condition of the transistor. Choosing the right Q point is crucial for linear amplification, as it ensures the transistor operates in the desired region without distortion. A stable Q point ensures consistent performance of the transistor amplifier. If the Q point shifts due to temperature changes or component variations, the amplifier may distort the signal or even stop working. That's why careful design and biasing are essential to maintain Q point stability in practical circuits. One of the most common uses of a BJT is as an amplifier. In this role, a small input signal at the base is used to control a much larger current flowing from the collector to the emitter. This allows weak signals to be amplified and made strong enough for further processing or output. Amplifiers are found in radios, televisions, and audio equipment. Amplifiers can be classified into different classes, such as Class A, B, OB, and C, based on their operation and efficiency. Each class has its own advantages and trade-offs in terms of linearity, efficiency, and distortion. Choosing the right class depends on the specific application and performance requirements. BJTs can also function as electronic switches. When used as a switch, the transistor operates in either cutoff off or saturation on mode. In cutoff, no current flows, and in saturation, the transistor conducts fully. This switching action is the basis for digital logic circuits and microcontroller outputs. The speed at which a BJT can switch between on and off states is important in digital applications. Faster switching means higher frequency operation, which is essential for modern electronics. Factors like transistor size, doping levels, and circuit design all affect switching speed. Biasing is the process of setting up the correct DC voltages and currents in a transistor circuit. Proper biasing ensures that the transistor operates in the desired region, whether as an amplifier or a switch. Without correct biasing, the transistor may not function as intended, leading to distortion or malfunction. A fixed bias technique uses a resistor connected to the base to set the base current. This method is simple and inexpensive but can be unstable due to variations in transistor parameters or temperature. It's mainly used in basic circuits where stability is not critical. In collector-to-base bias, a resistor is connected from the collector to the base. This setup provides some negative feedback, improving stability compared to fixed bias. It helps compensate for changes in transistor parameters, making it more reliable for practical circuits. Voltage divider bias is the most widely used biasing technique. It uses two resistors to form a voltage divider network, providing a stable base voltage. This method offers excellent stability against variations in transistor parameters and temperature, making it ideal for most amplifier circuits. Emitter bias adds a resistor in the emitter leg of the transistor. This resistor provides additional negative feedback, further stabilizing the operating point. Emitter bias is often combined with voltage divider bias for maximum stability in amplifier circuits. Temperature changes can affect transistor operation by altering current flow and voltage drops. Proper biasing techniques help minimize these effects, ensuring the transistor remains stable even as the environment changes. This is especially important in precision and high-reliability circuits. Stability factor is a measure of how sensitive the collector current is to changes in transistor parameters, such as beta or temperature. A low stability factor means the circuit is less affected by these changes, resulting in more reliable operation. Designers aim for low stability factors in critical applications. To improve stability, designers use techniques like negative feedback, emitter resistors, and voltage divider networks. These methods help keep the operating point steady even if the transistor's characteristics or the environment change. Stability is key for consistent amplifier performance. Thermal runaway is a dangerous condition where increased temperature causes more current to flow, which in turn raises the temperature even further. If not controlled, this can destroy the transistor. Proper biasing and the use of emitter resistors help prevent thermal runaway, protecting the circuit. Let's look at a practical example of biasing a BJT using the voltage divider method. By choosing appropriate resistor values, you can set the base voltage and ensure the transistor operates in the active region. This approach is widely used in amplifier design for its reliability and ease of implementation. Testing a BJT circuit involves measuring voltages and currents at various points to ensure proper operation. Using a multimeter, you can check the base, collector, and emitter voltages as well as the current through each terminal. This helps identify issues and verify that the biasing is correct. If your BJT circuit isn't working as expected, start by checking the power supply and connections. Look for incorrect resistor values or faulty components. Measuring the voltages at the base, collector, and emitter can help pinpoint where the problem lies. Systematic troubleshooting ensures reliable circuit performance. BJTs are used in a wide range of applications, from audio amplifiers and radio transmitters to digital logic circuits and power supplies. Their ability to amplify and switch signals makes them versatile components in both analog and digital electronics. Understanding BJTs opens the door to countless electronic projects. While BJTs are popular, field effect transistors (FETs) are also widely used. BJTs rely on current control while FETs use voltage control. Each has its own advantages and ideal applications. Knowing when to use a BJT or FET is a valuable skill for any electronics designer. BJTs are fundamental building blocks in many integrated circuits (ICs). They are used in amplifiers, oscillators, and switching circuits within ICs. Their small size and high performance make them ideal for large-scale integration in modern electronics. Despite their many advantages, BJTs have some limitations. They can be sensitive to temperature changes, require more current to operate compared to FETs, and may not be suitable for all high-frequency applications. Understanding these limitations helps in selecting the right component for your circuit. While newer technologies like MOSFETs and integrated circuits have become more common, BJTs remain important in many applications. Their robustness, simplicity, and high gain make them a staple in analog circuit design. Ongoing research continues to improve their performance and efficiency. To sum up, BJTs are versatile devices used for amplification and switching. Understanding their construction, operation, configurations, current gains, load line analysis, and biasing techniques is essential for designing reliable electronic circuits. Mastery of these concepts will serve you well in both academic and practical electronics. If you want to deepen your understanding of BJTs, consider studying advanced topics like frequency response, noise analysis, and power amplifier design. Experimenting with real circuits and simulation tools can also enhance your practical skills. The more you explore, the more confident you'll become in working with transistors. Congratulations on completing this unit on bipolar junction transistors. You now have a solid foundation in BJT construction, operation, configurations, current gains, load line analysis, and biasing techniques. With this knowledge, you're well equipped to tackle more complex electronic circuits and projects in the future.